Yeah, good morning. In this session, I would like to show you how to partition a given set of equations and also a given flow sheet. So these are the session outcomes. You need to identify the need for flow sheet decomposition or partitioning, and you should be in a position to partition the given set of equations or flow sheet. Why I am concentrating on equations is the same algorithm is going to be made use for even partitioning a given flow sheet. Of course, partitioning set of equations would also be required in the case when you are using equation oriented approach. So some typical definitions and concepts that we are going to make use. So for example, if you try to see, unit is nothing but module. Stream is usually considered as flow of material between two streams. And flow sheet decomposition. For example, if you try to see, when you have these 5 units, you know in sequential modular approach, the recycled stream is considered to be the tear stream. So let's see. This is what is meant by flow sheet decomposition. We did not solve all the 5 units as one single problem, because while solving this problem, the moment you consider this as the tear stream, so we will be guessing values for this stream and go on iterating these 4 units till we come to a convergence with respect to the tear stream. So if you try to include this unit 5 inside, unfortunately, you will be also doing unnecessary calculations involving in solving this unit 5 in an iterative loop, because S42 will be finalized only when S41, which is the recycled stream, when it comes to a convergent solution. So instead of solving all these 5 units as one single problem, we will be able to solve the first partition involving unit 1, unit 2, unit 3 and unit 4. Once we reach a convergent solution with respect to this first partition, then we will be able to solve the second partition, unit 5. So what is meant by tear stream is, a stream is considered to be tear by guessing values for that stream. And what is the calculation sequence? Guessing stream S41, I will be able to solve unit 1 because S0 and S41 are already known to us. Then you will be able to get S1, then solve unit 2, then solve unit 3, then unit 4, repeat until convergence of recycle loop, and then we will be solving unit 5. So this is a modular approach because at any given time we are solving only one unit at any given time. So these are some of the things. So if you look at this problem, how many partitions, how many recycle loops, and how many tear streams and what are they? So these are the typical issues that we have. Maybe in the next session, I'll be addressing some issues to calculate the tear streams. So for the time being, I am only concentrating on partitions. Once again, you can see that you will be able to partition this flow sheet into 2. So solving units 1, 2, 3, 4. Once you reach a convergent solution, because of this recycle, this will be considered as the tear stream. So you will be able to iteratively solve these 4 units, starting with an initial guess. You go on iterating till this recycle comes to a convergent solution. Then you will be able to finalize the stream. So given the input stream to this unit, you should be in a position to solve this unit to calculate the outputs. You know already that a rating model, given the input streams, equipment parameters, we will be in a position to calculate the output streams. So to answer these, how many partitions? 2. The first one is involving units 1 to 4 followed by unit 5. So there are 2 partitions. How many recycle loops? There is only one recycle loop involving units 1, 2, 3 and 4, but 5 is outside this recycle loop. How many tear streams? Only one tear stream, 7. So it can be, for example, if you start with 7, then I will be able to start with unit 1, followed by unit 2, followed by unit 3, followed by unit 4. For example, is there a possibility for me to tear stream 2 instead of 7? So if you tear 2, I will be able to solve unit 2 because its input is known to me, to calculate 3, then solve unit 3, solve unit 4, solve unit 1. By the time you know already 7. Now once you are able to solve unit 1, you will be able to get an update for this stream 2. So check for convergence, otherwise repeat this process. In the same way, you can convince yourself that there is a possibility of taking 3 as the tail stream or even 4 as the tail stream. So you have an option of selecting stream 2, stream 3, stream 4 and stream 7 as the tail streams. Of course, in the case of sequential modular approach, by default, the recycle stream is usually taken as the tail stream. Anyway, we will try to discuss some issues related to identifying the tail stream at a later stage. So, the computational sequence is going to depend on the tail stream that you are taking. If you take 7 as the tail stream, the computational sequence is unit 1, unit 2, unit 3, unit 4. If you take 2 as the tail stream, unit 2, unit 3, unit 4, unit 1. So, it is essential for you to identify the tail stream in order to decide the computational sequence. So, we will be looking at what is meant by partitioning, what is precedence ordering, why do we have to partition. So, as you can see in this example, without going into any analysis, we were able to partition by looking at it itself. But it may not be that easy in the case of complicated flow sheets or when the number of equations are more. So partitioning, what is the advantage? So instead of solving all the 5 units as a single problem, you are able to save some computational time in solving this in parts. Solving fewer number of units, you may be able to improve the rate of convergence as well. So you will be saving some computational time, that is an advantage. And probably, why do we have to partition? So it becomes easy in order to solve smaller problems than one single large problem. So these are some of the advantages that you will be able to get. So the algorithm that we are looking at can be used to partition equations or even flow sheets. The equations can be linear or non-linear. For example, consider these 5 equations in 5 unknowns, x1 to x5. There are 5 equations. So we are not going into the solution process. We are only trying to address how to partition these equations. So should we solve all these 5 equations for calculating the 5 unknowns as one single problem, or is it possible to divide this problem into subparts? That is what is meant by partitioning. Now you can look at this. F1 to F5 are going to indicate the equation numbers. X1, X2 to X5 indicate the variable numbers. This is what is meant by incidence matrix. It is very simple. You can use either an alphabet, a symbol, a number. The idea here is equation 1 is represented with only variables x1 and x4. So because x1 is available in equation 1, I am putting a symbol or number. Similarly, x4 is also represented in equation 1, but x2, x3, x5 are not present in equation 1. So similarly, you should be able to write this incidence matrix depending on what variables are involved in that equation. It need not be 1. As I said, you can use any symbol. So create this incidence matrix. But even from this incidence matrix, you may not be able to identify the partitions. So let me go into the next. This was the original incidence matrix. I have rearranged the rows and columns just like that. Okay. So F1, and I am writing F1, F4, F3, F5, F2. Remember F5, for example, when I write here, the incidence will also should be written, copied exactly. For example, we know in the case of F1, X1 and X4 are represented. So I am writing X1, X4. This order also got changed. Columns are also modified. So similarly, if I take F4, this is also having incidence with respect to X1 and X4. I write like that. So the moment you are able to transform this original incidence matrix into this form, I am not doing anything extra. Only for convenience, I am rearranging columns and rows. Now you can see clearly that this problem can be partitioned into 3. So because if you consider F1 and F4, they represent 2 variables and 2 equations. We should be able to solve these 2 equations to calculate the values of X1 and X4. Once I am able to solve this first partition, x1 and x4 values are already obtained. So I should be able to use equation 3 to calculate the value of x2. Once I know x1, x4, x2, I will be able to use equation 5 and equation 2 to calculate the remaining 2. Now solving all the 5 equations as a single problem, solving 2 equations followed by 1 equation followed by 2 equations is relatively much more simpler, especially when you are dealing with non-linear equations. So I am able to partition them. What is the order? Can I solve the last this partition first? How will I be able to solve this problem without knowing the values of x1, x4 and x2? So there is a particular order in which you need to solve these partitions. The order is, first of all, you solve this partition followed by this partition, then only you will be able to solve the last partition. So the order in which they are going to be solved is what is known as precedence order. Now, in the case of a few number of equations, it may be possible for us to do this manually. But if you have something like 1000 equations in 1000 unknowns, do you think this kind of an approach is going to be useful? No. So there is an algorithm, a very simple algorithm to do this. So let me present that. So I am not going into these details. So several algorithms are going to exist. So let us come to this algorithm later. First of all, let us deal with one example, and whenever there is a possibility or a requirement for this algorithm, I'll come back. So this is the original set of equations and I have already written the incidence matrix. So equation 1 has variables x1, x5, x6. Equation 2, so like that you should be able to write this. Now, before we apply that algorithm, we need to do one particular assignment, which is a prerequisite. You need to assign for every equation at least one variable, so that you will be able to take care of all the equations and all the variables. How this can be done? It can be done very easily. You try to identify the number of incidences in the column wise. So for example, if you take the number of incidences for x1, it is 2, x2 also 2, x3 2, x4 2, x5 4, x6 2. So identify the minimum number of incidences in the column. So if there are several such minimum, you can choose any one arbitrarily. So let me start with x1. Now x1, because it is appearing in equation 1 and equation 5 only, I can assign x1 to either equation 1 or equation 5. Which one should I prefer? Again, look at the number of incidences in the row. There are 3 incidences in f1, whereas there are only 2 incidences in f5. So take the minimum. So by this, I will be able to assign variable x1 to equation 5. This is what is meant by assignment. So let me complete this. Select first the column or row with the fewest or lowest number of incidences. If there are several such, you can choose arbitrarily and assign the other row such that it has the minimum number of incidences. Now you can see very easily. So I have assigned x1 to equation 5. Now look at the minimum number of incidences for the remaining variables for which you need to do this assignment. So again, x2, x3, x4 and x6 have the same number of minimum, which is 2. So let me take the case of x2. x2 can be assigned to either equation 3 or equation 4 because 3 has only 2 incidences while 4 has 3 incidences. I'll be assigning variable 2 to equation 3. Right? That is how I'll be doing. So in the same way, you should be able to go ahead and complete the assignment. Right? Okay. So x1 is assigned to f5, x2 is assigned to f3, x3 is assigned to x1, x4 is assigned to f4 and so on. You can see that all the equations are used, all the variables are used. Then only the assignment is complete. Now, what need to be done is having assigned, typically you can consider somehow I am calculating the value of x1 by using equation 5, let us suppose. Then the value calculated by f5 for the variable x1 need to be transferred or sent to equation 1 so that it can calculate the remaining variables. So this is what is meant by the information flow. In fact, this is what is known as graph theory. Now, what you can do is, let me go back to the algorithm. Now, for the start with any arbitrary node. Node is nothing but the equation. Form a string of nodes until a node reappears. So this is to be done once we create. I'll come back. I think we need to do one more step before we can apply the algorithm. So this is the assignment. Now I am writing F1, F2, F3, F4, F5, 6. These are considered to be nodes. Now the value of x1 that I am calculating from equation 5 should be sent to equation 1. Be careful about this direction. So there has to be an arrow to transfer information of x1 calculated from F5 to equation 1. So this is going to represent that. Right? Similarly, if you take F3, the value of x2 that I am computing from equation 3 should be sent to equation 4. So this is going to represent that. Similarly, the value of x3 that I am calculating from equation 2 should be sent to equation 4. So there should be an arrow. The direction is very important. The information is flowing from F2 to F4. That will take care of this. So like that you try to draw this digraph. This is called as digraph because there is a direction involved. Now we will be in a position to apply the algorithm to partition, which says start with any arbitrary node F1 to F6, go on tracing the output edge from each node until you come across with these two possibilities. A node may reappear when you are tracing the output edges. That could be one possibility. The other possibility is a node may appear that doesn't have any output edges. So accordingly, in the case of B, what you need to do is delete that node if it doesn't have any output and delete all the nodes that enter into it and put it at one place. In case of A, merge all the nodes appearing between the repeated node into a group node and treat it as any other node. So let me apply this algorithm on this digraph, which we have already drawn. So what I am trying to do, let me remove this. So now I am just putting it in the dotted line. I am starting with F1. You need not have to start with F1. Based on your convenience, you can start from any node of your choice. To explain what I am doing, I am following this path. Start with a node F1, go on tracing the output edge. I could go into this, or I can take this, or I can take this. So it is up to you. You can take any direction you want, but only thing that you need to do is whenever you start with a node, you need to always go along with the output edge from that node. So let us say I am starting from F1. By following this particular direction, I went to F6, and F6 there is an output edge. It came back to F1. So what is happening when I am tracing? This F1 is reappearing. So that is nothing but your case A. If a node is appearing in the string, right, then what you need to do, merge F1 with F6 or merge all the nodes that are appearing between this repeated node. So between the repeated node F1, F6 is appearing. So I need to merge F1 with F6. When you are going to put them together, obviously these edges will vanish because they are now combined into one single group node. So this group node also is going to be treated similar to any other node. So I am going to redraw this figure again. One more thing that I would like to tell you, how many edges are you going to have in this digraph to start with? So the number of edges that you have will be equal to the number of unassigned incidences you have in this incidence matrix. For example, the number of unassigned incidences are 1, 2, 3, 4, 5, 6, 7, 8. So there will have to be 8 edges, right, in this digraph. You can count. This is 1, 2, 3, 4, 5, 6, 7, 8. So this can be used as a check to identify whether you have created all the edges or not, because if you make a mistake here, there will not be a correct solution. Okay. So having done this first exercise, what I am going to do, this is the first part which is copied. Now I am trying to merge F1 with F6. When I merge that F1 with F6, these two will be vanishing. So you will be left with only 6 more edges. You can see 1, 2, 3, 4, 5, 6. Once again, I am starting with this for some reason. You could have started with any other node as well. I am starting with this. Now I am going in this direction because this is an output edge. I went to F5 and from F5 I came back to F1, F6. What is happening? So F1, F6 is getting repeated. And in between there is F5. What do you need to do? You need to merge F5 with F1, F6. When you merge F5 with F1, F6, these two will vanish. So you will be left with 4 nodes only when you redraw this graph. So this was the previous figure. Now because of the merger, now we are left with only 4 edges. Again, I am starting with F1, F6, F5. There is only one output edge. There is no option now. I have to go to F3. Then F3, I have only one output edge. I go to F4. I come back to F2. And then I come back to F4. Now what is happening? F4 is getting repeated. So what you need to do? You need to merge F4 with F2. When I merge F4 with F2, these two edges will vanish. So redraw the graph. This was the previous one. When you merge F2 with F4, we will be left with only 2 streams because these two will be vanishing. Connecting those two. Now I start with F1, F6, F5, go to F3, go to F2, F4. So for convenience, I have taken all case A. Now I am coming up with case B. Where do you go from here? There is no output edge from this node. That is the second case. When you have no output edge, what you need to do? Delete this node and also delete the edges that come into it and put this information at one place. So I have to delete this and I need to note down what is the node that I am deleting first. Okay. So when I delete this, what will happen? I am left with only these 2 nodes. Again, when I start with F1, F6, F5, I end up with F3. This doesn't have, okay, let me redraw this for convenience. So I am left with this. Starting with F1, F6, F5, I end up with F3. So it doesn't have any output edge. So what I need to do? I need to delete this as well as this edge. So I am left with only this and the deleted node is written here. This is the first deleted node. This is the second deleted node. This is the last deleted node. Because I don't have any more output edges that will automatically be deleted and written here. Right? So the original problem now is partitioned into 3. F2, F4, F3, F1, F6, F5. Now, what is the order in which they need to be solved? So the last deleted node should be solved first, followed by the previously deleted node, followed by the first deleted node. So the order will be in this direction. So the last deleted node is the one that need to be solved first, followed by the previously deleted node, followed by the previously deleted node. So this is the partitioning and the precedence order, the order in which they need to be solved are something like this. So wherever you have the choice of starting with any arbitrary node, you have the choice of tracking the output edges. So whatever you try to do, the partitioning solution is always going to be unique. Mathematically, this can be proved. But sometimes the precedence order need not be unique. For example, if you try to see this, now the original problem is divided into 4 parts involving equation 1, equations 2 and 3. This is the second partition, this is the third partition, this is the fourth partition. So one possibility is solve the first partition followed by second partition. By the time you solve the first partition, you will be knowing the value of x1. So you have 2 equations in 2 unknowns. You should be able to solve this. The moment you solve equation first partition, because you know this value, you should be able to solve P3. The moment you solve second partition, you will also be knowing the value of x2. you should be able to solve this partition. So P1, P2, P3, P4. This could be the precedence order, or after solving P1, I can also solve P3 instead of P2. So there is an order difference. There are two possibilities here. So the precedence order need not be unique, but the partitioning is always going to be unique, right? Okay, this is what is meant by partitioning. Now, this is as far as equations are concerned. Now, when you look at, let us suppose this is the flow sheet that I have, right? A, B, C are going to represent the models or equipment involved in a flow sheet. Probably if you consider A, it can be considered something like a storage tank wherein you are drawing material. So something like that. So how should we solve all these units as one single problem, or is there a possibility to partition this into parts? One advantage with partitioning flow sheets, having done partitioning of equations, is the flow sheet, because there is a flow of material in a particular direction. So the flow sheet itself can be considered as a digraph. How are we able to draw the digraph in the case of partitioning equations? You need to create the incidence matrix, you need to complete the assignment. Based on the assignment, you need to draw the graph. But all these steps need not be done in the case of a flow sheet. You already have a flow sheet, which is something similar to a digraph. You will be in a position to directly apply the algorithm. What does the algorithm says? You can start with any arbitrary node, go on tracing the output edges from that node until you come across two possibilities. What are the two possibilities? You may come across, when you are tracing this output edges, a node may reappear in that string. In such a case, you need to match all the nodes appearing between this repeated node. The second possibility is you may have a possibility of a particular node which doesn't have an output edge. In that case, you need to delete that. So let us start with applying the algorithm directly on this flow sheet. So starting with A, I may be doing it in a particular fashion. It doesn't mean that you are required to start with A. I could have started with K for that matter. Try to do that and see whether you are able to end up with the same solution. So I am starting with A, go to B, go to D, go back to A. So what is happening? This particular node A is reappearing. So this is case A, first possibility. What should you do? You need to merge A, B and D. A should be merged with B and D. When you merge A and B and D, these streams will vanish. This will represent the number of the stream number for convenience. So when you merge ABD, now 1, 8, 9 will vanish. So you need to redraw the graph. So that's what happened. ABD, you can see. So whatever is going from B now will be going out from ABD. Whatever that goes from D now will be going from this group node. So there are two output edges from ABD, which are 2 and 10. So you can see 2 is here, 10 is here. The remaining will be as it is drawn. So while redrawing this graph, be careful not to omit any stream. Now once again, I may be following in a particular order. I start with C. So I am following this path, C to E, E to H, H to I to C. So what is happening? This C is getting repeated. So I need to merge unit C with E, H and I. So when you merge these, automatically these streams will be together in one unit. So they will disappear. So whatever goes now from C or whatever comes to E will be now coming to CEHIC. CEHI. So let me redraw this graph by merging C with E, H and I. So I'll be eliminating 3, 4, 5, 6, 22. All the other strings will have to be written as it is. So this is what I have done, and redraw the graph. Now once again I am starting with CEHI. I am going in this particular direction. I could have gone in this direction as well. Try that. So I am going to F, L, M, N and then CEHI. So this node is reappearing. So in between we have F, L, M, N. So we need to merge these units with CEHI. When you merge F, L, M and N, these streams will disappear. So redraw the graph. So this is ultimately we are left with this. Once again, I am starting with this group node. I am going to K. I am going from this direction. You could have gone this in order to reduce the number of redraws. I am going in this direction. CEHIFLMN to J, K and then back to this. Once again you can see this node is again a pairing. Right? So what you need to do? You need to merge J and K with this. When you merge J and K, of course all these streams will vanish. So you are left with this. Now you start with ABD. You end up with this. Now you have nowhere to go. There are no more output edges. In such a case, you have the second possibility. You need to delete this, put that information at one place and also delete the incoming edges to this. You are left with ABD. So the problem is partitioned into two. The unit C, E, H, I, F, L, M, N, J, K will form one partition and the second partition will involve units A, B, D. What is the order in which you have to solve them? The last deleted node is the one that you need to solve first, followed by the previously deleted node. So you have two partitions and the order is ABD followed by the second unit. So solving all the units together compared to solving a small partition would be definitely easier. It helps in achieving faster convergence the moment you go to the next partition. By the time you would have solved some streams, so that will help you to reach a quicker convergence with respect to the other partition. So this is what is meant by partitioning, especially in the case of complicated flow sheets like this. It may not be possible for us to analytically or by having a look at it, it may not be possible for us to identify the partitions like what we did in the case of some simple examples. So with this, I would like to stop this session.